Okay, last day of section 12.8 with complex numbers. And we're going to start out by talking about graphing complex numbers and the complex number plane. So notice that in the complex plane we have a real axis and we have an imaginary axis rather than an x-axis and a y-axis. But plotting the points is pretty much the same type of thing. Notice here we have the point 3 minus 2i. So we're going 3 units out on the real axis, and then we're dropping down 2 units on the imaginary, and we have our point. Okay? And when we talk about the absolute value of a complex number, we're talking about the distance between the origin, between 0, 0, and that complex number out here at 3 minus 2i. So the distance, or the absolute value of a complex number, is simply found by taking the square root of a squared plus b squared. It's distance, so it has to be a real value. So we don't use the I portion. We're just taking the a and the b. So when we look at the absolute value of 3 minus 2i, we're really looking at the square root of 3 squared plus 2 squared. Okay? And that gives us 9 plus 4. And that's where we get this square root of 13 for the distance. So if we look at a couple more examples here, in part A we've got the complex number negative 5 plus 3i. And notice that that is plotted here over in quadrant number 2. The negative 5 is negative 5 units to the left or on the real axis. And then positive 3i, so 3 units up. And the absolute value, or the distance from 0 of that point, is the square root of negative 5 squared plus 3 squared, and that's where we get this square root of 34. Okay. In part B, we have the 6i. So 6i means there's no real part, which means we're not moving left or right, and all we're doing is simply going up 6 units on the imaginary axis. And the absolute value of 6i becomes 0 squared, because the a is 0, plus 6 squared, so I get square root of 36. So we have a distance of 6, and that makes sense. We went straight up 6 units, so that's the distance from the origin, is just those 6 units. So let's look at a couple of examples here. We've got 5 minus I in part A. So if we want to plot that with our real axis over here and our imaginary axis going vertically, 5 minus I means we're going to move over 5 units on the real axis and down 1 unit. So we'd have this point right here at 5 minus I. If I want the absolute value of 5 minus I, that is going to be the square root of 5 squared plus negative 1 squared, which gives me the square root of 25 plus 1, or square root of 26. Okay. In part B, we've got negative 3 minus 2i, which means we're going to go negative 3 on the real axis, and then minus 2 means we're going to drop down 2 units, and here's our point right down here. And the absolute value of negative 3 minus 2i would be the square root of negative 3 squared plus negative 2 squared. Well, negative 3 squared is 9, negative 2 squared is 4, so I get square root of 13 for my distance from 0. Okay. So plotting the points is pretty much the same as plotting an ordered pair, only instead of x and y, it's real and imaginary. And then finding the absolute value. Remember, absolute value always represents distance from 0. So we just take the square root of a squared plus b squared. So the last thing we're going to talk about with complex numbers goes back to solving quadratics. And understanding that every quadratic equation has a complex number solution. It's just that sometimes we only get the real portion. And those are the things that we've been looking at up to this point. Okay? But if we look at this example down here of 2x squared minus 3x plus 5 equals 0, when we go to the quadratic formula and we go through these steps to simplifying it, notice we get down here and we've got a negative underneath our radical. Okay? So remember, the negative underneath the radical really means we can pull out that negative as the I times the square root of 31. So what happens there is then we're splitting it. We're taking the real portion, which is the 3/4, and then we're taking the imaginary portion, which was that square root of negative 31, or this I square root of 31, and we're writing that as a complex number in that a plus bi form. Okay? So let's kind of work through another example again. So if we look at example A, 3x squared minus x plus 2. So to solve that, we're going to take the opposite of b, so the opposite of negative 1, plus or minus square root of b squared minus 4 times a times c, all divided by 2 times a. So as we start to simplify that, the opposite of negative 1 is 1, plus or minus square root, negative 1 squared is 1, 4 times 3 is 12, times 2 is 24, so I really have 1 minus 24, which is negative 23, all divided by 6. So that's going to be 1 plus or minus, the negative becomes I, so it's I square root of 23, divided by 6, and now we're going to split it. We're going to have 1/6 plus or minus the square root of 23/6 times I. And that would be our solution to that quadratic equation. Notice that both solutions here have an I, so that both solutions are imaginary, which means there's no real solutions, but there are two complex number solutions. So again, with no real solutions, remember it would mean that that graph is never actually going to intersect the x-axis. If we look at problem B and we start to solve, we'd have the opposite of b plus or minus square root of b squared minus 4 times a times c, all divided by 2 times a. So as we simplify, the opposite of negative 4 is positive 4, plus or minus square root, negative 4 squared would give me 16. 4 times 1 times 5 would be minus 20, which means I'm going to have negative 4, okay, all divided by 2. So that's going to be 4 plus or minus, the negative is I, okay, so this would be like I square root of 4, but the square root of 4 is 2. So when I split, I would have 4 over 2 plus or minus 2 over 2i, which gives me 2 plus or minus 1i. And there is our solution. Okay. So we can use these complex numbers and this idea of I, and this I being the square root of negative 1. Okay. So remembering that I is square root of negative 1, to come up with solutions to quadratic equations that we weren't able to do anything with before because we had a negative under the radical. Okay. So we'll do some problems in class tomorrow dealing with graphing these complex numbers and solving these quadratics where we're going to end up with a complex number as our solution.